Welcome. In this video, we start a new chapter, Chapter 5, Combinatorics. 5.1 is an introduction to combinatorics, and it sort of sets the stage for everything that's about to come in the rest of the chapter. Three big ideas that we will look at: finite structures, organization in counting, and combinatorial equivalence. Before I hit these 3 points, though, there's one section I want to talk about, maybe a section 0. That's just basically, what is combinatorics? In combinatorics, the big question is how many? Here are some examples of combinatorial questions. A pizza shop has 9 possible toppings for its pizzas. How many pizzas are possible? A matching test contains 10 questions, and each answer must be used exactly once. In how many ways can a student answer the questions if every question is answered? Suppose that 80 babies are born in the month of September in a hospital, and we record the date that each baby is born. In how many ways can this event occur? An organization has 10 male and 16 female members. How many ways can you form a committee with 6 people if the committee is required to have at least 2 females? In all of these questions, we are counting things. That's what combinatorics is all about. How do you count? Section 1, Finite Structures. There are 4 different types of problems that we will run across in this chapter. Let's talk about these 4 different problems. Imagine that you draw 3 letters from among A, B, C, D, E. You can do this in 4 different ways. Maybe you ask, how many lists of length 3 can you make, where repeats are allowed? These are ordered lists. Here we go. Here's what they are. These are all the ordered lists where I draw 3 elements from A, B, C, D, E. So you can see that, well, first of all, everything has length 3. Repeats are allowed, so I have elements like A, A, B. And the order does matter because even though I have A, A, B, I also have A, B, A, which is the same 3 letters in a different order. And I also have B, A, A just below it there. So I count all 3 of those as separate things to be counted. So these are ordered lists. Another question we might ask is, how many lists can you make that contain 3 distinct letters? Kind of like before, but now I don't allow repeats, distinct letters. And there are fewer of those. These are all of them. So again, I'm drawing from the letters A, B, C, D, E, and this is the number of ways I can draw 3 of those letters and put them into some kind of an order where I don't allow repeats. We see A, B, C, but I won't see A, A, B. On the other hand, the fact that order still matters means I will see the different rearrangements of A, B, C. There we go. So in fact, that first column contains all the rearrangements just of A, B, and C. A third problem you might ask is, how many sets can you make that contain exactly 3 letters? In this case, repeats aren't allowed because in sets we don't have repeated elements, but also order does not matter. I see A, B, C, but I won't see any rearrangements of A, B, C. A set doesn't care what order its elements are in. And lastly, I might ask, how many unordered lists of length 3 can you make? Now let me explain an unordered list. These are lists where repeats are allowed, but mixing up the letters doesn't count as a new list. For example, AAB and ABA count as the same list. These are also called multisets or bags. Here we go. Here are the unordered lists in our problem. Take a look. I see AAB, but I don't see ABA or BAA. I like the word bags. It's pretty descriptive. It's kind of like I have an A, and a B, and I just throw those 3 things into a bag. You can imagine you go to the store and you buy 2 apples and a banana, and it doesn't matter the order that you buy them in. You know, when you get out of the store, you put those 3 pieces of fruit in your bag, and that's all that really matters. So we have these 4 finite structures. We have ordered lists, permutations, sets, and unordered lists. In the sections that follow in Chapter 5, we'll learn how to count these things systematically. So, 4 types of finite structure. There is an organization to these. First of all, sometimes order matters and sometimes order doesn't matter. For ordered lists and permutations, the order of the objects makes a difference. ABC is different from BCA. On the other hand, sometimes the order doesn't matter. In an unordered list, that is a bag or a set, we often write those things in alphabetical order because that's just one way to write them, and we don't need to care about the order of things. So we need to determine, we sort of think, does order of the elements matter or does the order not matter? The other thing to think about is repetition of the elements allowed or not? On the top row, when repetition is allowed, this is where you see the word list. So keep an eye out for list. Ordered list, unordered list. When I list things, I'm allowed to make repetitions. On the bottom row, when repetition is not allowed, these are the permutations and the sets. All right, so here are 6 different word problems, and I don't want you to find the solution, but I'm asking, what kind of a solution are we looking for? Consider those 4 finite structures that we've just been looking at, and for each word problem, figure out which finite structure would best help us answer the question. All right, this is a pause and try slide, so pause the video, try your best, and play the video again when you are ready to check your work. All right, let's take a look. A is an ordered list. B, ordered list. C, unordered list, a bag. There we have our apples, bananas, and oranges. D, ordered list. E is sets, and F is permutation. Big idea number 2, organization in counting. Basically, establish a systematic method when listing possibilities. Sometimes problems are small enough that you can solve them brute force. You don't need complicated equations. You can just write out all the possibilities and determine a solution. Here are 3 examples that are small enough where you can actually just write out all the answers completely if you can figure out a good way to do it. So establish a systematic method. Think about this. Again, we'll pause the video and see if you can solve these things, and then I'll go through a solution on my own. All right, give this a try. Okay, let's take a look. How many permutations of the letters in set are there? So systematically, maybe I would start all the permutations that start with S, and then I'll make all the permutations that start with E, and then all the permutations that start with T. Well, if I start with S, then E and T remain. So S, E, T, and S, T, E. I can move those around. If I start with E, then S and T remain. So how about S, T, and T, S. And then finally, if I start with T, then S and E remain. So I'll say S, E, sort of keeping them in the order that they appeared originally. The S came before the E, and then T, E, S. So this is one way you might do this, a systematic way to write out all the permutations. Example 2, how many ways can one order a sandwich and a drink if there are 4 sandwiches and 3 drinks to choose from? There are a couple ways to think about this problem. One might be almost like a multiplication table. Imagine sandwich 1, sandwich 2, sandwich 3, sandwich 4 on the left, and then across the top, drink 1, drink 2, drink 3, and then every entry in this multiplication table corresponds to a choice of 1 sandwich and 1 drink. 4 on the left, 3 on top. 4 times 3 is 12. There are 12 possibilities. Sometimes people use a tree to organize their counting. They might say, well, I have 4 choices for sandwich, so sandwich 1, sandwich 2, sandwich 3, sandwich 4, and then for each choice of sandwich, I have 3 drinks to choose from. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can count 12 combinations altogether there. And then example 3, how many different subsets of 1, 2, 3 are there? So maybe to do this systematically, we start with how many subsets have no elements. How about the empty set? And then we'll go through the subsets that have 1 element. So 1, 2, 3, and then the subsets that have 2 elements, 1, 2, 1, 3, 2, 3. And then the subsets that have 3 elements, well, there's only one of those. 1, 2, 3. There we go. And so I've made all the different subsets there, so I can count them. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of those. Our third big idea in this section is combinatorial equivalence. This is a deceptively powerful idea. You see mathematicians employ this a lot professionally. Two lists have the same length if there is a one-to-one correspondence between them. Here's an example. So set 1, counting problem number 1, might be, how many ways are there to distribute 3 coins, say a silver dollar, a dime, and a penny, to 10 children? So that's a counting problem. How many ways are there to distribute these 3 coins to the 10 children? Here's another counting problem. How many numbers are in the set 0, 1, 2, 3, all the way up through 999? One of these problems is extremely easy. It's immediate. Okay, this is the second one. Okay. We know that the answer to that is 1,000. Maybe I can establish some kind of a one-to-one correspondence between these two problems. And in fact, I can. So let's see how we do that. Let's number the children 0 through 9. So child 0, child 1, child 2, all the way up through child 9. What might distributions look like? Well, I have a silver dollar and a dime and a penny. And conceivably, this silver dollar, I need to give it to one of the kids. So I give it to child number 5. And the dime, I'm going to give that to child 8. And the penny, I give that to child 2. There, so there is one distribution of those 3 coins. Here's another one. I don't have to give the 3 coins to the 3 different children. I can give the silver dollar to child 7, and the dime to child 7, and then the penny to 0. Or if I really want to, I can give all 3 coins to the same child. Child 8 gets the silver dollar and the dime and the penny. Now, each distribution corresponds to some number in that set from 0 to 999. What do you think? Elements from the set, well, this distribution of 5, 8, and 2 looks a whole lot like the number 582. And the distribution where child 7 gets the dollar, child 7 also gets the dime, and child 0 gets the penny, that looks a lot like the number 770. And 888 on the left looks a lot like 888. So I've made, there we go. So I've made a function from distributions to elements in this set. Now I need to reverse the process. Well, if I have the number 582, how about if I say that whatever digit is in the hundreds place, that child gets the silver dollar, and whatever number is in the tens place, that child gets the dime, and whatever number is in the pennies, it is in the ones place, that child gets the penny. And so this function actually goes in both directions. And if I pick a random number from the set 0 to 999, how about 617? That corresponds to the distribution. Child 6 gets the dollar, child 1 gets the dime, child 7 gets the penny. And of course, I can work that back to the right. So every distribution corresponds to a particular element in the set. Every element in that set, 0 to 999, corresponds to some particular distribution. There is a one-to-one correspondence between these two sets. So they have the same number of elements. Now, the problem number 2, that was very easy to count, and so now I know a solution to number 1. How many ways are there to distribute these 3 coins? There are exactly 1,000 ways. So it's kind of a neat idea. Establishing a one-to-one correspondence between two different sets. One of those sets might be easy to count. So if you know how many elements are in that, then you know how many elements are in the other set also. All right, how about some practice? Use a one-to-one correspondence to explain why 1 and 2 below should have the same answer. So take a couple minutes, try your best, and start the video again when you are ready to check your work. Let's take a look. So in problem A, we're looking at distinguishable arrangements of the letters A, B, A, B, A, and 5-digit binary sequences with exactly 3 ones. All right, so let's take a distinguishable arrangement of A, B, A, B, A. So A, how about if I just start with that? A, B, A, B, A. And I need some kind of a binary sequence, so zeros and ones, with exactly 3 ones. Well, I have 3 A's on the left, so how about if I make my A's into ones and my B's into zeros? There we go. So given any arrangement of A's and B's, I have a corresponding binary sequence with zeros and ones. All right, and if I just pick a random arrangement of zeros and ones, as long as it has 3 ones, about 0, 0, 1, 1, 1, that will correspond to some distinguishable arrangement of A, B, A, B, A. So in this case, B, B, A, A, A. So there we go. So this function I've created shows me how to turn arrangements of A, B, A, B, A into binary sequences with 3 ones, and it shows me how to reverse the process. So I have a one-to-one correspondence between those two sets. So they must have the same number of elements. For part B, let's see, 2-element subsets of the set 1, 2, 3, 4, 5. So let me just make something up. How about 1 and 3? What set should that correspond to in terms of 3-element subsets? So do you see what it is? How about if I take all the numbers that aren't in that set? So this becomes 2, 4, 5. And it's a function. I mean, given my 1, 3, I can really, that gets mapped onto 2, 4, 5. There's only one thing it can map onto. And let's see, if I pick another one, how about 2, 3? Then that maps onto the set 1, 4, 5. And does the process work in reverse? If I start with a 3-element subset, I can map it onto a 2-element subset by looking at the numbers that are missing. So for example, let's just try, how about 3, 4, 5? That corresponds to the set 1, 2. And so we see it, and it goes back and forth in both directions. So we have a one-to-one correspondence going in both directions. Therefore, these two sets have the same number of elements. Kind of a cool idea. All right. In this introductory section, in 5.1, we've looked at finite structures, organization in counting, and combinatorial equivalence. 3 foundational ideas that we will see again and again and again throughout this chapter 5. All right, and this is a good place to stop.